Constructing the seemingly impossible requires confronting physical limits. Engineers routinely encounter unforeseen geological conditions, extreme environmental forces, and materials pushed to their breaking point. These challenges demand not just innovative designs, but often counterintuitive solutions that redefine what is achievable. Consider the Burj Khalifa, reaching 828 meters into the sky. Its primary adversary was not just gravity, but wind. Traditional skyscraper designs face escalating wind loads with height, leading to immense swaying and structural fatigue. The solution involved a unique Y-shaped buttress core, meticulously sculpted to disrupt wind vortex shedding. This strategic tapering and angling of the tower's faces confused the wind, preventing the formation of organized vortices that would otherwise exert powerful, resonant forces capable of tearing the structure apart. Beneath the English Channel, the Channel Tunnel presented a monumental battle against water and geology. Tunnel boring machines, or TBMs, had to navigate unstable chalk marl, a permeable rock prone to collapse and water ingress. Engineers developed and deployed specialized shielded TBMs, operating under significant pressure. These machines simultaneously excavated and erected precast concrete segments, forming a watertight lining immediately behind the cutting head, sealing against the immense hydrostatic pressures of the seabed. This concurrent excavation and lining process was critical to maintaining tunnel integrity and preventing catastrophic flooding. The expansion of the Panama Canal, adding a third set of locks, faced the challenge of water conservation in a region with fluctuating rainfall. The original locks relied on gravity to fill and empty, releasing vast quantities of fresh water into the oceans. The new Neo-Panamax locks integrated water-saving basins. For each lock chamber, 3 adjacent basins collect and reuse 60% of the water during each transit, reducing freshwater consumption by millions of liters per day. This system necessitated complex hydraulic controls and massive valve mechanisms to manage the immense volumes of water efficiently. Building the Palm Jumeirah in Dubai required transforming open sea into stable land. The primary engineering problem was the liquefaction potential of dredged sand and the long-term stability of the artificial islands. Instead of compacting the sand from the surface, a process called vibrocompaction was employed. Giant vibratory probes penetrated the sand to depths of up to 26 meters, causing the particles to rearrange into a denser, more stable configuration. This deep compaction was essential to prevent settlement and ensure the structural integrity of the foundations for future construction, mitigating the risks of seismic activity or storm surges. The construction of the Three Gorges Dam across the Yangtze River necessitated managing the displacement of the river itself during construction. This involved a multi-phase cofferdam strategy. Initially, a temporary diversion channel was excavated and 2 massive cofferdams were built upstream and downstream. These structures created a dry work area within the riverbed for the dam's foundation and central sections. Once the central dam was sufficiently advanced, the diversion channel was gradually closed, forcing the entire river flow through temporary outlets within the partially completed dam structure, allowing the remaining sections to be built in sequence. The Millau Viaduct, a cable-stayed bridge spanning the Tarn Valley in France, confronted extreme wind forces and the immense weight of its concrete deck. The solution involved prefabricating the steel deck sections on land and launching them incrementally across the valley, supported by temporary piers. Once the deck was in place, the permanent concrete piers, the tallest of which reaches 343 meters, were constructed. The cables were then systematically tensioned, transferring the deck's load to the slender, flexible piers, which were designed to flex with wind rather than resist it rigidly, an aerodynamic approach minimizing structural stress. The International Space Station, assembled in orbit, solved the problem of constructing a large, complex structure in microgravity. Each module was designed to be launched individually, and then robotically or astronautically docked and connected. The critical engineering challenge was ensuring precise alignment and robust connections in the vacuum of space, far from Earth's gravity. Universal docking adapters and standardized interfaces allowed different components, often from different nations, to fit together seamlessly, forming a cohesive and pressurized habitat. This modularity permitted incremental expansion and replacement, crucial for a project spanning decades. The Large Hadron Collider, designed to accelerate protons to near light speed, required maintaining an ultra-high vacuum across its 27-kilometer circumference. Any stray gas molecules would collide with the proton beams, causing signal loss and reduced efficiency. Engineers developed multi-stage vacuum systems, employing roughing pumps to reduce pressure initially, followed by turbomolecular pumps and ion pumps to achieve pressures equivalent to outer space. This stringent vacuum environment was critical for minimizing beam interaction with residual gas and allowing for precise particle collision experiments. Crossrail, London's Elizabeth Line, navigated the immense challenge of tunneling beneath a densely populated urban environment with existing Victorian-era infrastructure. The primary concern was ground movement and subsidence affecting historical buildings and active subway lines. Engineers utilized highly precise TBMs equipped with real-time monitoring systems. These TBMs could adjust their trajectory and grout injection rates to actively manage ground pressure and minimize settlement, ensuring the stability of overlying structures. Targeted compensation grouting was also employed to inject material into the ground to counteract any detected movement. The Hoover Dam, a massive concrete arch-gravity dam, faced an unprecedented thermal problem. The hydration of cement during concrete pouring releases significant heat. If poured in a single mass, the dam would have taken over a century to cool, leading to severe cracking due to thermal expansion and contraction. The solution was to pour the dam in interlocking columns, each a maximum of 1.5 meters thick. Embedded within these columns were networks of 2.5 centimeter steel pipes through which chilled water circulated, artificially cooling the concrete and accelerating the curing process, thus controlling thermal stress and preventing catastrophic failure. Constructing artificial islands in seismic zones, such as Kansai International Airport, introduced the problem of soil liquefaction during earthquakes. The airport was built on a man-made island composed of sand. To mitigate seismic risks, engineers developed a deep soil improvement method. They drove long, hollow piles into the seabed, then filled them with sand and vibrated them to compact the surrounding soil. This process, known as sand compaction piles, increased the density of the sand layer, significantly reducing its susceptibility to liquefaction during seismic events and ensuring the island's long-term stability. The Øresund Bridge, connecting Denmark and Sweden, transitions from a bridge to an underwater tunnel. This junction, an artificial island, presented unique challenges concerning water flow and environmental impact on the sensitive Øresund Strait. The tunnel sections were prefabricated on land as immersed tube elements, each weighing up to 55,000 tons. These massive elements were then floated into position, precisely sunk into a dredged trench, and joined underwater. This method minimized disruption to marine life and vessel traffic during construction, while the tunnel allowed for unrestricted shipping access above. High-speed rail networks, like Japan's Shinkansen, face the issue of intense air pressure waves when trains enter tunnels at high velocity. This tunnel boom effect can cause discomfort to passengers and structural damage. The engineering solution involved careful tunnel entrance and exit profiling, known as hoods or flared portals, which gradually compress the air rather than abruptly displacing it. Furthermore, tunnels are often designed with varying cross-sections or ventilation shafts to dissipate pressure waves, effectively mitigating the sonic impact and ensuring passenger comfort. Designing buildings for extreme seismic loads and highly active fault zones, such as Taipei 101, required an innovative approach to dampening vibrations. Instead of relying solely on structural rigidity, engineers incorporated a massive tuned mass damper. This 660 metric ton steel sphere, suspended between the 87th and 92nd floors, is connected to the building's structure by hydraulic pistons. During an earthquake or strong winds, the pendulum oscillates out of phase with the building's movement, absorbing and dissipating kinetic energy. This actively reduces sway by up to 40%, enhancing stability and occupant safety. From stabilizing shifting sands beneath the sea to taming the thermal expansion of concrete, these projects reveal engineering as a constant negotiation with nature's forces. Each megastructure stands as a testament to the methodical application of scientific principles, creative problem solving, and the critical decisions that transform audacious visions into tangible realities.